Hello, I am Dr. K. Meena, Associate Professor and Head, Department of Mathematics, Arulmigu Palaniadavar Arts College for Women, Palani. Welcome to my presentation on ring theory. In this video, I am going to define ring definition, properties of ring, integral domain, field, skew field, and two theorems on integral domain. First, come to the definition of ring. Let R be a non-empty set with two binary composition denoted by additively and multiplicatively. Then the system R, plus, dot is said to be a ring if it is satisfies the following conditions. The system is nothing but a non-empty set together with two binary operations addition and multiplications is said to be a algebraic system. Is said to be a ring if it satisfies the following conditions. Number 1, R, plus is an abelian group. In abelian group, we are having 5 more conditions. Closure property, associative property, existence of identity, existence of inverse, and commutative properties. Coming to the second one, R, dot is semi-group. So once again, semi-group we are having two conditions. One is closure property and the second one is associative property. So first condition abelian group with respect to addition, second condition semi-group with respect to multiplication. And third condition is distributive law holds. A dot B plus C equal to AB plus AC. That is a left distributive law. And B plus C dot A equal to BA plus CA. This is a right distributive law. For all A, B, C belong to R. Whenever a non-empty set together with two binary operations plus and dot satisfying all these three conditions, the set R, plus, dot is a ring. Next, coming to the properties of ring. Ring with identity. A ring R is said to be a ring with identity or ring with unit element if there exists an element 1 belongs to R such that 1 dot A equal to A dot 1 equal to A for all A belongs to R. Second property, commutative ring. A ring R is said to be a commutative ring if AB equal to BA for all A, B belong to R. It means if you want to define commutative ring, first of all it should be a ring and after that it satisfies one more condition AB equal to BA for all A, B belong to R. Next, ring with zero divisors. A ring R is said to be a ring with zero divisors if a non-zero element A belongs to R, then there exists another non-zero element B belongs to R such that either AB equal to 0 or BA equal to 0. In a ring R, take two non-zero elements. To calculate the product of these two non-zero elements, then the answer is 0. These two non-zero elements are also called zero divisors of R. Next, the examples of commutative rings: integers, real numbers, even integers, integer modulo n, that is Zn, or commutative ring. But Mn of R, if n greater or equal to 2, is not a commutative ring. We will take two elements in Mn of R, n greater or equal to 2, that is two matrices A, B belong to Mn of R. The product of AB is not equal to the product of BA. So the commutative property is failed. The set Mn of R is a ring but not a commutative ring. And the next example of ring with zero divisors. We take integer modulo 12, that is Z12. Z12 that is equal to set of all 0, 1, 2, etc. 11. We take two non-zero element in Z12, that is 3, 4 belong to Z12. What is the product of 3 into 4? 12. So the multiplicative modulo value is 12 is 3 dot circle 4 is 0. So we take two non-zero element, the product is 0. These two non-zero elements are called zero divisors in Z12. So Z12, in Z12 3, 4s are non-zero, that is zero divisors of Z12. And 2 into 6, the value is 12, therefore 2 dot circle, that is a multiplicative modulo 12 value is 0. 2 dot circle 6 is 0. Similarly 4 dot circle 9, so 4 into 9 value is 36, so 4 dot circle 9 value is 0. And 3 dot circle 8, so 3 into 8 means 24, so 3 dot circle 8 value is 0. So in Z12, 2, 3, 4, 6, 8, 9, these are all the zero divisors. Next, ring without zero divisors means a ring R is said to be a ring without zero divisors if AB equal to 0 implies either A equal to 0 or B equal to 0. These are all the properties of ring. Next, definition of integral domain. So in order to define integral domain, first of all it should be a ring. After that it should be satisfies three more conditions. First one, R is commutative ring. Second one, R has unit element. Third one, R is having without zero divisors. So we have already discussed about commutative ring without zero unit element and without zero divisors. So next, coming to the definition of field. A ring R having at least two elements, that is a non-trivial set. So a ring R having at least two elements is said to be a field if it is satisfying the following conditions. So first one is R is commutative. Second one, R has a unit element. Third one, every non-zero element in R having multiplicative inverse. Then we say that this ring R is called a field. So the ring satisfying three conditions. First one, commutative ring and with the unit element, and every non-zero element of R having multiplicative inverse, the ring is called a field. Next, skew field. Skew field means a ring R having at least two elements is said to be a skew field if it satisfying the following conditions. So first one, R has a unit element. Second one, every non-zero element in R having a multiplicative inverse. So every time in every definition we are saying in a ring, it means we define integral domain, field, skew field, zero divisors. First of all, it should be a ring itself. After that, it should satisfy some more conditions. So next, theorems on integral domain. We see the proof of the following theorems. Statement of the first theorem is Zn is an integral domain if and only if n is prime. So integral domain means three conditions are satisfied. There are any rings satisfying three conditions. Number one, commutative ring. R has a unit element. Third one, R is having without zero divisors. Without zero divisors mean a ring is said to be without zero divisor if AB equal to 0 implies either A0 or B0. This A comma B belong to R. Okay. So first, the proof of the theorem, Zn. What is Zn? Zn means integer modulo n. That is Zn equal to set of all 0, 1, 2, etc. n minus 1. So what is the prime? Prime means the number divisible by 1 and itself, or n is prime, n equal to product of 1 into n or n into 1. Okay. So first part of the theorem, first assume that Zn is an integral domain to prove that n is a prime. Converse part, we assume n is prime, we have to prove that Zn is an integral domain. So first see the first part, that Zn is an integral domain. We claim that n is a prime. Suppose n is not a prime, we conclude that the contradiction. Okay. So first n is, suppose n is not a prime means composite number. So composite number, the product of two integers. So then n equal to pq, where 1 less than p less than n and 1 less than q less than n, because this p and q not equal to 1 and n. Therefore this p and q belong to Zn. Zn equal to set of all 0 to n minus 1. So this pq belong to Zn. Zn is an integer modulo n. So the value of the product of the value pq value is n. So the p dot q value is 0. The remainder is 0. So the value is a multiple of n. So the remainder is 0. Therefore p dot circle q is 0. Any two, we get the result, any two non-zero element of product value 0, these two non-zero elements are zero divisors of the set. The set is Zn. So Zn has two non-zero elements, p and q. This p and q product is 0. Therefore this p and q are zero divisors. So the condition p and q zero divisor, so Zn is not an integral domain. So which is a contradiction, because the given assumption is wrong. Our assumption is Zn is an integral domain. So which is a contradiction, because n is not a prime. Okay. Therefore n is prime. Conversely, suppose n is prime, we claim that Zn is an integral domain. Zn is an integral domain means three conditions needed. R is the set is commutative ring with a unit element and without zero divisors. So first, to prove that Zn has without zero divisor, that is has no zero divisor. So zero divisor, no, without zero divisor means AB equal to 0, let A comma B belong to the set. This A, assume AB equal to 0 implies either A0 or B0. So let A comma B belong to Zn. Then A dot circle B equal to 0. That is AB is a product of n. That is multiple of n. So AB equal to Qn, where Q belongs to Zn. That is, this AB is divisible by n. So n divides AB. AB is divisible by n. Therefore this n divides AB. Given n is a prime, so n divides either A or B. Therefore n divides A or n divides B. So n divides A means in the integer modulo n, the remainder is 0. Therefore A equal to 0. So n divides B means in this element B belongs to Zn. So the value is, the remainder value is 0. Therefore B equal to 0. So given we get the result A dot circle B equal to 0, we get the result either A0 or B0. Therefore Zn has without zero divisor, that is has no zero divisor. Next, third condition is satisfied. First two conditions is clearly satisfied, because Zn means set of all 0, 1, 2, etc. n minus 1. Take any two value as the product value. For example, 5 into 5 dot circle 2 value same as 2 dot circle 5. Okay. So commutative law is satisfied, and 1 belongs to Zn. This set has a unit element. Therefore Zn is a commutative ring, has a unit element, is having without zero divisors. Therefore Zn is an integral domain. For example of the above theorem, take Z7. 7 is a prime number. Z7 means integer modulo 7, that is set of all 0, 1, 2, 3, 4, 5, 6. Take two non-zero elements, 3 dot circle 4. What is the value? That must be equal to 3 into 4. Product of 3 and 4, 12. The 12 is divisible by 7. The remainder is 5. The quotient into divisor plus remainder 3 into 4. The value is, the remainder value is 3 dot circle 4. The value is 5. So 6 dot circle 5, the remainder is 2, etc. So any two non-zero value in Z7, the product non-zero values, the answer is non-zero. So this is without zero divisor, and 1 belongs to Zn, 1 belongs to Zn, and 2 the A comma B, that means 3 comma 4 belong to Z7, 3 dot circle 4 value and 4 dot circle 3 values are same, so commutative satisfied. So Z7 is a prime number and Z7 is an integral domain. So the given theorem, example of the above theorem. Next theorem, any field F is an integral domain. We know that field means in a ring satisfying 3 conditions. So first one, the ring is commutative and unit element, and has a unit element, every non-zero element in the ring having multiplicative inverse. We need 3 conditions. The ring is called a field. So given F is a field. To prove that the field is an integral domain. So given assumption, field 3 conditions are given. Therefore F has a commutative with identity. It is enough to prove that F has a no zero divisor, or F without zero divisor. So let A comma B belong to F, A B equal to 0 and A non-zero, to prove that B equal to 0. Since F is a field, so multiplicative inverse exists. So A inverse belongs to F. So AB equal to 0, in A inverse of AB is also 0. Using associative law, A inverse of AB is equal to A inverse A into B. So A inverse A equal to A inverse, that is A into A inverse, or A inverse into A, the value is 1. Therefore 1 dot B equal to 0, 1 non-zero, therefore B equal to 0. We get B equal to 0. So therefore AB equal to 0, this A non-zero implies EB equal to 0. We get the result. A ring R is said to be a without zero divisor if AB equal to 0 implies either A0 or B0. So the condition is satisfied. This F has without zero divisor, or F has no zero divisors. So 3 conditions are satisfied. This F is a field F is a 3 conditions are satisfied. Commutative ring with identity element and without zero divisor. Therefore this field F is an integral domain. But the converse is not true, and that is integral domain need not be a field. For example, Z is an integral domain but not a field, because 1 and minus 1 has multiplicative inverse. 2 has no multiplicative inverse, since 2 into 1 by 2 value is 1, but 1 by 2 does not belong to Z. So Z has no multiplicative inverse except 1 and minus 1. The condition is failed. Therefore Z is not a field but integral domain. Okay. Thank you.